if you have like text data, like what are the ways that you can kind of like work with it in order to get it into like a machine learning model and then actually do something useful with it. So those have been the 2 topics so far. Cool. Go ahead and get started, I guess. So I just said this, but I'm John. We're Funkhaus. I'm going to be talking about naive Bayes, practical naive Bayes. We'll talk about what that is if you don't know. But basically, like our thinking here is, I just said this, but I'm not an expert on this stuff. I'm sort of like self-taught, and like Luke is very helpful to teach me things. So you might have to bear with me a little bit on like details, or if you have questions or whatever. My thinking is just like having gotten some feedback from the group and like the talks that we've done before is just like that we want to have like material that's a little more like practical, that you could, maybe some of you are like, technical like programmer types and like, but don't know that much about like the statistics side of it or like what have you. And that's kind of like my background. So I wanted to put together something that was like kind of approachable for someone who knows how to program but may not know that much about like the mathematics of how this stuff works and everything. So just to give an outline of what we're going to be talking about here. Sorry, messed my thing up. Oh, it's still not working. Nope, okay. I don't know what happened. I might just have to, that's fine. Okay. Anyway, so just to give you an outline, we're going to go over, like, I'm going to define what naive Bayes is. And I sort of started this with the idea that we were going to cover a whole like section of statistical learning, but it ended up not being that way at all. We're just going to cover naive Bayes, but hopefully that's okay. We'll have enough to talk about. We're going to talk about what it's good for and when to use it. And then we're going to walk through a whole example problem and with a bunch of code that's written in JavaScript, not because it's everybody's favorite language, but because it's, it's very common. Most people know how to work with it, so hopefully if you're into that and that's useful for you, then you'll be able to sort of walk through the code with me. And then we'll talk about some other applications and different, less traditional ways to use it. So, first of all, oh my God. The tech guy that couldn't figure out, there we go. Okay, cool. So, about me, I just did an introduction, but I am the head of Funkhaus Ithaca. I like machine learning, but I don't do it professionally. But hopefully I can teach you some stuff. You can email me there if you have anything to talk to me about, or find me on GitHub there. And actually there's going to be a couple things at least that we'll talk about. You can get to the code. Cool. Anything else? I think we went through the whole thing. I also wanted to mention that, I was just talking about how this group is like sort of a beginning thing, and we're still getting it figured out. One thing is that we would love to get more feedback from you guys, so I think that everyone probably is part of the meetup group here and probably can be reached through the mailing list, I assume. So I'm going to send out a little thing with like a Google form there with topic submission. If anybody wants to talk about something or would like to hear a talk about it, we'll have a form set up and I'll send it probably tomorrow out to the newsletter group, just to like anyone, the more feedback that we can get, the better. Just like, or tell us here afterwards, it doesn't matter. Next month we're going to have someone speaking about, we actually have our first like non-Funkhaus person going to do a topic. And they're going to be talking about A/B testing and sort of like that side of things. If you work with the web, I think, like we do, I think that's really interesting. So that will be, actually not next month, that's next time. That'll be in May, I think. Cool. Okay, so what is naive Bayes? Let's get started there. It's not just one single algorithm. It is a whole family of algorithms, and they are all probabilistic models. So you've got multinomial naive Bayes, Bernoulli naive Bayes, Gaussian naive Bayes. They all do different things. We're only going to cover a very basic version of this today, but hopefully you'll have like a good idea of what you can do with it. So it's a probabilistic classifier. So what does that mean? It means it's able to sort of predict a probability of a set of classes or categories or labels or however you want to do. We'll get into that in a little bit, but that's the basics of what it does. The example that we're going to be walking through is text classification. Okay, gone through these things. Family of classifiers, probabilistic, text classification, that's what we're going to be talking about. And that just meaning that you have some body of unknown text, you have some data set of unknown text, and you need to do something with it, and how do you use naive Bayes to help you figure out something about your text. Naive Bayes itself can also be called sometimes simple Bayes or independence Bayes. It's got its name because it's based on Bayes' theorem. Thomas Bayes, statistician, 1700s, made Bayes' theorem. It sort of like orbits around that, and we'll get into that a little bit. And what else is it? One of the main features of it, which is something else we'll talk about a little bit later, is conditional independence. That's the naive part of naive Bayes. So Bayes is Thomas Bayes. The naive part is that it sort of makes broad assumptions about your data that features are not necessarily are independent from labels in some way. So we'll get there in a minute, but that's the broad overview. So probabilistic classifiers. This is what, oh, by the way, there's a link down here. I don't know if you guys can even see this actually, the way that we have this set up. And this is the slides, and there's going to be some stuff in here that we're linking to, but I have this on every slide as we go through, and I'm sorry if that's not super visible to some of you guys, but if you have a laptop and you want to follow along there, or follow the links or whatever. Okay. Classification. This is what we might see when we're looking at an ordinary classification model. So we've got sample. Again, ours is going to be text data, and we're going to be talking about language classification specifically, so that's why the word French is in there. So we may have like a set of documents here, or a collection. We're going to make our model with naive Bayes, or not with naive Bayes. We're talking about ordinary classification here. You have some form of model. You have documents with unknown languages. You put it through there, and you're going to get, it's going to just tell you outright what it thinks. And this model is basically some form of function. So this is what ordinary classifier is. It's binary, basically. It's going to tell you yes or no, is it this label, right? Most of the time. With probabilistic classification, it's going to work a little bit more like this. You have your documents, you have your model. It has awareness of a set of sort of different classes or labels that you've given it, and it will basically give you a probability, like a spectrum a little bit of like what it actually thinks, and some confidences to go along with it. So then once you have that, you can derive your answer that way. Obviously the easiest way, if you have like this type of thing, this type of result, then it's very easy to just to say, okay, the biggest one is it. That's one of the main ways. There's two primary ways that we're not actually going to cover that much because it's a little bit outside of the scope. But basically there's different ways to interpret what you do with that data. But basically the point is, really good benefit of probabilistic classification of this kind when you have this data is that it tells you its confidence outright. Not every machine learning model does that. It's really nice that it says, I am 75% confident that this document is French, because then you can have some kind of threshold. You can say, well, if we're above 95% confident of a particular language, then maybe we want to act on it. If we're below that, maybe not. Maybe we want to do something else. That'll be a little more relevant later. So next, we're going to get into our example problem, basically. What are we looking at here? So again, we're going to do language classification. So this is an example of what that might look like. So we have two documents with small amount of words here. They're in different languages. We presumably have some data set of documents as well that we use with our model. But basically, we're going to have, we want to basically build a function that will be able to take in one of these documents. It's just like a random set of words. Not random, but it's a set of words. And tell us what language it thinks it is. So this is a really good problem for naive Bayes for reasons we'll get into. But this is the problem that we're doing, but you could think about this. There's like a number of different problems that you could use all the exact same code that we're going to use to solve. And so some of those would be like spam detection. If you're trying to, say you have emails or something, you're trying to detect if it's spam or not spam. It's going to work exactly the same. Another one would be maybe you have like an archive of articles, and you need to sort them into categories. You have some that are categorized and a lot that are not categorized. you could use this same exact strategy to sort of like sort them into categories. Another thing that naive Bayes has been proven to do pretty well is take text and determine the gender of the author, whether it was written by a male or a female. Interestingly, that's something that is somehow possible. So just weird different things that you can do with this stuff. But basically, have some text and determine something about it. So before we get into how we would do this with naive Bayes, I want to talk about how you might think about this just normally, because obviously we can look at these words and probably make a pretty good guess at what language each one is. Neither are English, so it's probably not immediately obvious. But how do you do that when you're doing this? Well, you can sort of tell. The first thing you notice is that they have some words in common, right? So that is super not helpful, because if there's a word in both, that's not going to help you identify it. So we first want to ignore those. And more importantly, there are some words that are not in common. And some of them, just these that I've pointed out, may be ones that you've that are common words that are like easy to recognize. So you can see para and por over here. Those are definitely like common Spanish words. Do over here, common French word. So we could make the assumption maybe just off of that this one is French and that one is Spanish, which is correct, but maybe, so if that works for us, maybe we want to expand that into, a whole strategy. So how would we actually sort of manually program that with no machine learning involved? Maybe we take the strategy that we just did, identifying a couple words, and set a whole bunch of rules, right? So maybe we just basically have a bank. We go through every word and we see, okay, so we had some words that were in common. So those are uncertain words. We have de and la. We don't know what language those are in. But we have some words that we know that do is not a Spanish word. It's only a French word. So maybe we put that into a bank of certain French words. And then we have these other words that are definitely Spanish words, right? So maybe then we go through each document and we look at each word and we say, okay, if it's uncertain, we don't know. But if it is certain, then we can decide definitively, okay, yes, this is definitely the language. Of course, there's going to be problems with that, right? So first is what does certain mean? If you come across the word do, are you definitely 100% sure that it's French? Maybe if your only options are French or Spanish, but that's also a German word. So maybe you encounter something that's not even in your data set, and you need to be able to take that into account. So treating each word as completely atomic, like definitely in this language or not, is not a good solution. Let's see, what about words that, or a sort of different problem where the data will overlap a lot more? Maybe if you have French and Spanish or French and German, there's not going to be that many words realistically that overlap. But maybe if you have Spanish and Portuguese, you're going to have a lot of overlap. Maybe if you're trying to do spam detection, everything is in the same language and almost all the words will be very similar, and you just have to pick out a few very particular ones. So again, not super viable for that. What if one language is quoting another? What if we're in French and someone, breaks into a Spanish quote in the middle of a French document? Does that mean that it's immediately Spanish because we see some Spanish in there? No. So basically what we need is a few things. We need to have rules that are not binary, rules that won't bind us to okay, you see this thing, it means definitely it is this thing, right? So we sort of need a scale of probability for these things. More importantly, this is kind of the manual ways, an assumption that we're going to do this manually, and we can't do that. We want it automated. We're lazy. We want to just dump a ton of data into a model and have it do everything for us. But importantly, on that note, our computer is lazy too. Not really, but we have a finite amount of CPU, right? And so there's a lot of words. If you're going to account for every single word in every single language and then try and analyze it against that set every single time, you're going to have a lot of problems, right? So we need to do something that can sort of make good, reasonable assumptions without needing to cover every single possibility. So that's called generalization. Cool. So that covers that. So hang Oh yeah, so let's look at how we might do this a little bit more in like the naive Bayes type of way. And so to start there, we're going to talk about some natural language processing basics, which is something that we've covered in talks before, so sorry if this is a little bit review, but we got to do it. First is that we have these two documents, so we're going to sort of define what document even is. What is a document? A document is a collection of terms, a collection of words, and we're going to have a lot of documents. Some of them will have labels and some of them won't have labels. And so the entire universe of documents that we're aware of is going to be called our corpus. So that's every single document that we have. And then we have single documents. And for our definition, a single document is essentially just a set of words, but we're going to call them unigrams. So when in natural language processing, when we might be thinking about how to break up an entire set of text like this, the most obvious, I guess, is to just go through and split by space, right? Maybe we just like break it up, everything by space, and then we get a bunch of words. But if we do that and we analyze words independently, then we lose context, right? So that's a trade-off. If we don't want to lose context, we could pair words together. We could go through and split it, but we could join every set of two words, these two, these two, these two, these two, and look at those. But the problem with that is that that's going to start introducing a lot of entropy into our system, or complexity, right? So the more context that we get, the more entropy that we're going to have. So for our case, there's other cases where you might want to consider a bigram approach, a trigram approach, multiple words joined together. We're going to do unigrams, just isolating one single word. But there's other stuff that we can do besides that to actually like reduce the entropy here. So we can make some decisions about, do we care about punctuation? Do we care about casing? Do we care that this says Yahoo with an exclamation point versus just Yahoo? What do we actually care about there? So we're going to take some steps in the beginning to just reduce entropy. We already just talked about unigrams versus bigrams or any other n-gram. That is all about context. Really, we're just trying to capture meaning of words. For our purposes, doing language detection, we're going to capture meaning. So in terms of meaning, are these three any different? Your, all caps versus these other ones? If we just remove the punctuation there and make them all lowercase, that's an easy way to do it, right? If we have just a four-letter space to create a word, and we count capital letters and non-capital, we could make 7.3 million variations. But if we reduce that just to lowercase, that brings it down automatically to 450,000. So that's a huge, huge reduction. So there's things that we can do that will, from a computational standpoint, automatically save us a lot of work. So your. But this is for our language detection problem. But what about a different problem? What if you're trying to detect if something is spam or not spam? Are these different, right? I think so. Probably something in all caps is definitely has a lot more meaning. Or what if it has 20 exclamation points after it? That obviously would be something that would fall into the more spammy category. So for that reason, for that particular problem, a lot of people will choose to keep the casing and punctuation intact for that type of thing. Another thing we can do is tokenization. And so that, again, on the concept of like really just capturing the meaning of a word. If we have these three words, imagine, imagination, imaginary, are those really different? Not really. They kind of all have the same meaning. And so we're trying to capture the meaning. So possibly there are algorithms that will help you do this. There's a lot of tooling in Python and JavaScript and whatever you're going to do that are tokenization libraries that would basically chop off the end of all of these words and just make them all imagine with no E. And so that basically allows you to isolate that as like one concept that when you're actually going through and analyzing this stuff, all three of those would be linked to the same idea there. For our approach, all we're going to do for this problem is no tokenization. We're just going to split by space. We're going to strip all punctuation, and we are going to make them all lowercase. This is what that looks like in JavaScript. Super easy. We have a function called tokenize text. You just go lowercase, strip out white space, trim the edges, split by space, and then make sure everything in it is unique. So that's our tokenization function. Real easy. Cool. So next, what are we talking about next? Next we have to talk about probability, I guess. So once we have all those tokens, we have just like a whole collection of tokens. We need to find a way to actually go through and look at them and compare them to the entire collection that we have, right? So if we take this and we run it through our tokenization function, we know that we're going to get an array that's basically just each individual word, no punctuation, all lowercase. So that's good. But now we need to take that word and associate it with a particular label. So the important thing to know here is that what we want really is we have the word do here and we're trying to figure out language, so we're just going to look at this one word at a time. We need to figure out what are the odds, because we see this word, that this document is a particular language. That is not an intuitive problem to solve, really. It's really easy to go the other way around. So when we look at this, if you're not used to this, which I'm not because I'm kind of mathematically challenged, this is just stating the probability. So when you see P in these parentheses, you're saying the probability of something. And when there's a pipe in the middle like this, you're saying the probability of something dependent on something else. So what's the probability of the word do, given that we know that the document is French already, right? So that is really easy to figure out. Here in this example, maybe these are, this is just not real data, but maybe this is a really common French word that appears in every single French document that we have, right? So we may have a collection. In this example, our entire universe is only French and Spanish, so we just have French documents and Spanish documents. We come across this word, and we can easily look across our entire collection and say, how often is this unigram found in a French document? Maybe 100% of the time. That's just counting them up because we have labels for all those already, right? But how often is it in a Spanish document? That's obviously going to be a lot less because it's not a Spanish word. But maybe, it's French is quoted sometimes here and there, so maybe it only appears 5% of the time. So that's easy. But that doesn't help us. That 100% that do is French doesn't tell us that 100% chance that our document is French. So what we need to do is we need to turn it around. We need the other way. We need the probability that this document is French, given that we've seen the word do. And that is basically the core of Bayes' theorem. Yes?
So to get those percentages, you've gone through and physically labeled a series of documents already in your set.
Yes.
They've gotten those percentages.
Exactly. Yes. Good question. Yeah, that's an assumption that I sort of skipped over here. But so when we're solving this problem, we're going to have training data, and then we're going to have our live data that we're actually trying to figure out, right? So we may have 500 documents that we've pulled off the internet that are, that we know are Spanish. They're from Spanish websites. We have 500 French documents that we know are written in French. And so we will have done some pre-processing to go through, run all of those documents through our tokenize function that you saw a minute ago, and then basically keep track of all of the tallies. We'll actually look at the code of how we do that in a minute. But you're right, at this point, that's the assumption. So we can easily look through that data, just loop through everything, look for a single particular unigram, a single token, and try and figure out what the odds are that it's in there, right? So if do appeared in 50% of, half of the French documents, then we'd have 50% probability that it ends up in French. But again, not helpful, because that doesn't mean that there's a 50% chance that this document is French. It just means that that's how often it appears in French. So going back to this, we need the other way around. We need how probable is it that this document is French, given that we've just encountered this one word. So that's what Bayes' theorem is doing, right? And so this is Bayes' theorem right here. I think we're going to I think my next slide is going to break that down a little bit. This, I guess, like, you know, it's not super important that you like understand the math. It's not that it's a very complicated equation, obviously, or anything, but like the point is that you just need to understand that that's what it does. It just flips around that probability. But to walk through this, so this is sort of like what we were seeing before. We have the probability of one thing given another, and we need to, you know, flip that around, right? So, the first part right here is the probability. You know, this is essentially what we'd be trying to solve for, right? So this would be like, what's the probability that this is French given that I see this particular unigram? And that's going to be equal to this equation here. So the next step would be, well, that's the probability that, that our word is in a French document, which again, back here is this, right? We already know that. It's easy because we can look across all of our documents. We know that do is in 100% of documents, right? So there, we know that one, easy. We multiply that by the probability, oh man, which I should have just done this with the proper labels, right? Okay, we do that with the probability of a French document. So A is our label, right? So we do that by multiplying it by the probability that we will encounter a French document in general, right? So if we have exactly 500 French documents and exactly 500 Spanish, that's going to be 50% probability. And then we divide those two by the probability of this word across our entire corpus. So in both French and Spanish, what's the probability that we encounter this word in general? That's how you do it. Again, doesn't matter if that, you know, the actual math of that. But at this point, you know, I guess, so the algorithm that we're going to do, I mean, we'll walk through this in a minute, is just, that's all we do really, is just like we take a single word and we use this information that we have to run this transformation on it, and then we get a probability, one single probability of the probability that this document is French given that we've seen this one word. And then we do that for every single word, and we total them up, and we have a probability for our document as a whole, right? But given that, you might be thinking that that is sort of a stupid assumption, right? Because we're looking at just every single word individually. What do I care about the single word do, right? Like we've completely lost our context. You know, we're basically just going through and taking single words by themselves and assigning some probability to them, right? And the ones that are, you know, are less common get a higher probability. The ones that are, the ones that are, yeah, we'll go back to that in a second. Basically, we lose context, right? The point is that we lose context. If we're detecting spam and we come across the words erectile dysfunction, you would think that that's a real spammy thing to receive in an email. But that's kind of, you know, basically if you break that up and we're only looking at the word dysfunction, what does that matter? How useful is it that we have the word dysfunction to like know if we're actually spam or not, right? But this is kind of like the reason why it's going to work, I guess, right? Is because we take our words, so this is, again, this is a French document. These two words up here, and these aren't like real numbers, but this is sort of how it would work given the example of just two languages. So we take these two words, and these are only French words that are not often seen in Spanish, and those will get assigned very high probabilities of being French by Bayes' theorem, right? And this word, which is a word that's common between both languages, will get a very uncertain probability. It'll basically get assigned, I have no idea, 50-50 chance if this is French or Spanish. And so that's sort of the magic of the whole thing, right? Is that there's sort of a decorrelation happening here where we take the words that are actually matter and are unique to the language, regardless of how common they may be in the language or not, and we assign a probability to them where they basically don't matter. And then we take the words that are very unique to the language and are not found in other languages specifically, and we assign a high probability to them. So this is from article by Brock Kember. I'm probably not pronouncing that right, but Machine learning, naive Bayes part 1. The reason that naive Bayes classifier works well for document classification is that it decorrelates the number of times a word is seen in a given language from its statistical importance. So that's basically just saying, like, this is all probability, it's no magic, and the common stuff that's common between languages gets weak significance, unique words get strong significance, right? So that's it. This, by the way, a lot of my code that you're going to see here comes from this article, so I'd recommend checking that out. It's really good, just like primer in general. Okay, here's another example. We were talking about just to step away from the language detection thing and sort of illustrate this with a different problem. There's this book called Data Smart. That's another one of my big recommendations for like just beginning, and I have a link to that later, but just introductory like data science type stuff. By this guy, John Foreman. He is like runs the data science department of MailChimp. And they have a service called Mandrill with this horrifying logo up here. And that is basically a service to like send emails, right? That's all it is. But if you name your company Mandrill and then you're automatically reading a stream of Twitter feeds, tweets about the word mandrill, you're going to get a lot of noise because mandrill is also a primate. It's not just your company. So say that your task here was to read a stream of tweets for the search term mandrill, and you had to figure out which ones are about actually the service that you care about because you work for Mandrill, and which ones are actually about the monkey, right? So we have our first example tweet here. Just from this random person. I don't know who these people are, but I must have forgotten to mention that Mandrill has a strict privacy policy and unlike Facebook, doesn't like to share its data. Clearly about the service Mandrill, that's the one we care about. Here's another one. Very first thought I had this morning. If I had a zoo, I'd definitely have a monkey named Lynn Mandrill Miranda. That one we don't care about because that's about a monkey. So when we're thinking about the naive Bayes way of doing this and we're trying to like classify these tweets and put them in the categories of like something I care about versus something I don't care about, unlike with language detection, there's going to be a lot of words in both of these that don't matter at all, right? So I can look at this tweet and say must, has, doesn't, mention. None of that has anything to do with Mandrill or being a service or a monkey, right? However, there are some words like privacy and data that you probably will not often see associated with a monkey, but you will often see associated with an email service, right? And similarly, we have these first, morning, definitely. We don't care about those words. We don't care about most of the words. But zoo and monkey, we do care about. So that's what we're getting at here, basically. Words that are red here will be closer to a meaningless probability, equal probability across classes. Words that are green will be higher probability biased towards one class, and that's what we care about. Okay, cool. This all has to do with Zipf's law, which is just sort of the idea here, as I understand it, is that just that in any given language, the most common words are very, very, very common. So this is, in the English language, the word the is way, 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 way more common than all these other words, right? So it's sort of a, exponential curve there, basically, that we see, where the most common words are super common. So if you see the all the time, it doesn't necessarily mean that it's a super important word, and that is sort of the thing that naive Bayes is helping us determine. Just because it's seen everywhere all the time, maybe in multiple languages, does not mean it's important. It may not be important for our problem at all. So there's that. Okay, back to our example. So basically, getting back into JavaScript here, this is our training function. So again, it's assumed that we have some collection of data, right? We have a training set, so we have a whole corpus of documents that are labeled French, documents labeled Spanish, documents labeled English. In our example, we're actually going to care about those 3 languages, not just the 2. And then we have an incoming document. We're going to look at this just like one single document is coming in, and we need to make a prediction. But first, we have to train based on the data that we have. So this is our training function. Basically, just to walk through this step by step, first thing we do is we have the text coming in, we have the label. So this is the single document coming in and the label. We run this function called register label, which is not shown here, but basically that's just gonna persist the count of that label to a database of some kind, any kind of storage. It doesn't have to be a database, any kind of storage. Basically, it's gonna persist. It's gonna say, okay, we have the word do coming in here and the label French. We're just going to say that we have this label French, right? So that way we recognize that it exists in our entire world of documents, because this training function doesn't know starting out. Yes?
So is that going to do like you were talking about, where you know that you have exactly 500 French documents, exactly 500 Spanish documents, which is incremental?
Yeah, well this actually, this one alone actually is just giving our algorithm the awareness only of the label. So like this is a bit generalized, so that this is written so that you don't know how many labels there are in the world. You're just going to start looping through all the documents you have and feeding it. So you could have German, French, Spanish, like whatever, anything coming in here. And so this just basically needs to register a global list of like, okay, French is a word that we even know exists. And so then we take the words that are in the text and we run it through our tokenize function, which we already saw. That's just going to like clean it up and split it and lowercase everything. Then we get some words here, and we're going to loop through those words. And we are going to increment stem. So increment stem is just going to say, like, stem is our token, right? It's our unigram. It's our single word. That's the word do in the example I've been using, right? So we say increment stem. The word do has been seen once for the label French. Just keeping a tally. That's all we do there. Once we're done looping through all those, now we increment doc count, which is your question, Sander. That's what we're doing here. So we're basically saying, like, now we have seen one French document, you know, and then we do this again. We have a new word, you know, we go through, we register the label if it hasn't been seen before. We split up the words. We take every single word and we keep tally of how many times we've seen it per language, and then we increment the times that we've seen that language in general. That's it. That's how you train in naive Bayes. So one big benefit in naive Bayes is that that's really easy as far as like machine learning training algorithms goes. It's really light and pretty simple to do. Basically, you have your set of data, and all that you're really doing is doing some accounting. You're just like looking for your different words and keeping track of certain things. At the end of the training, we're going to have all the labels in our corpus, which is going to be English, French, Spanish in this example. We will have word occurrences, so we'll be able to easily say how many times was the word vous seen in a French document. So like maybe that was 30 times or something. We'll be able to easily tell that. And then we'll have the total documents that we have for each label, like you were saying, Sandy. That's it. Training is done. Okay. Now we have that, and now we have some documents coming in unknown languages. And so how do we actually make a prediction on each of those given the training data that we just set up? So first thing here, just going to walk through this line by line. Really simple. This is just some accounting. This is really easy. This is just a loop where we go through and say, okay, for each label, we look at this label and we say, how many documents do we have in this label? How many documents do we have in other labels? So if we have 3 languages, 100 of each label, we'll say, this is French. How many French documents do we have? 100. How many not French documents do we have? 200. That's it. Then this is just saying, how many documents do we have in total? That number is 300 in our example, right? So that's it. We're just setting up some variables there. Underneath that, we're going to get into the actual meat of our prediction here. So when we do a prediction, we're on a single document. We're going to loop through all the labels in our corpus. So we only have 3, so we're going to basically do this 3 times. So for each language, we're going to do the following things. Number 1, just set our label equal to the single label. So label is now equal to French in our scenario of walking through a single document. And we're going to set up a log sum. This will eventually, sorry for those that can't see, this is just setting a variable to 0. This basically is just saying, like, okay, that's where we're going to hold the score. So we're going to walk through every document or every word in the document, and then we're going to keep score right there, and we'll eventually have a log sum for each label, basically, because we're in the middle of looping through each of our languages here, right? Okay. Next, this is the magic, the real like meat of the algorithm here. We're going to walk through this one section at a time. So right here, first we are looping through every single word. So this is our single tokenized word in the document. We set that to word. We set a variable here that says how many times have we seen this word total in the entire corpus across all languages. That becomes stem total count. If it's 0, we don't care about it, so we're just going to move on. That has to do with a problem with naive Bayes, a very well-known and debated one, as I understand it, called the zero frequency problem, which is basically if you encounter, you may have words in your training data or your words in your live data that you have not come across in your training data. And what do you do about that? Because that will be 0, which will basically wreak havoc on the whole rest of the algorithm. So you need to like have ways of doing that. Some people think that you should just ignore it. Some people think that it's good to basically make a prediction based off of a normal distribution of how often that word shows up. So that's all that's happening here. We basically say, here's our word, here's how many times we've seen it, and do we care about it or not? Assuming that we do, in this if-else statement, we move down to this stuff, which is like the real core of the thing, right? We have word probability. So that is, if you remember in those first few slides, what's the probability that do is in a French document? 100%. We see it in everyone. So that's what this is. What is the probability that the word that we're seeing is in the label that we're worrying about right now, that we care about? After that, what's the inverse of that, right? What is the probability that it is in some other label other than the label that we care about? And then, finally, this wordicity variable here is the magic of Bayes' theorem, really. So that's just flipping it around and saying, given those two things, the probability of it being in our label and the probability of it being in some other label that we don't care about, what is now the probability that this document is label given, that this word is in it? That's it. There's something important on this line, this wordicity, that's basically, we're making the assumption here that, that all of our labels are equally probable, which is not realistic, but for this simple example, it's going to work fine for our purposes, but that's just one caveat that I wanted to point out here. And then, underneath that, I just put a little bit of Lodash dependency in there for brevity, but in the actual, there's like a JS fiddle where you'll be able to actually see all of this in action. That's not in there, but don't worry about it. So all that we're doing is just basically saying if it's below 0.01, then make it 0.01. If it's above 0.99, make it 0.99. We just clamp it to that value because we're about to run it through a logarithmic function. If it was 0 or 1, it would do all kinds of bad things. So I'm just going to clamp it. And so that's that. And then here, lastly, we now have done that in a loop for each individual word. And now down here, we need to find a way to take this single word and add it into our log sum. So we have log sum going on here. Basically, so this is really just like a practical thing down here. At this point, this is where the important stuff happens. Single word, what's the probability that this document is labeled based on the word? And now we just need a practical way to basically, because we have 100 words or 500 words or 1,000 words in this document, we need a way to take all of those probabilities and put them all together without taking into account the amount of words that we have, because obviously it doesn't matter if a word has 3 words in it or 300 words in it. That doesn't matter for the language. So that's what this is doing here. Normally, you basically multiply all the probabilities that you have together and then divide by the multiplication of the inverse. That's normally how you would basically get all the probabilities together. However, we are, as I understand it, in the world of computers, and that's not a great idea because of floating point underflow. And so basically, when numbers get really small, computers can no longer understand them, and we would get maybe an inaccurate result. So this, and also because adding is a little bit easier on our computer than multiplying. So the way that we're going to do it here is this way. Again, this is another one of those things that it's not super important that you understand exactly what's going on here. It's more important that you understand that we have a whole set of probabilities now, one for each individual word and token in our document, and now we just need to combine them all so that we compare it to other things. So at the end of this, we get our score for this single label. So the odds that this is French, you know, is going to be some number between 0 and 1, right? And that is our probability. And we will, since we're looping here, we'll have that for each language. So we will, at the end, get something like this. Basically a JavaScript object. That's what this function here produces. That says all of the labels in the known corpus and the probabilities of each. So in this example here of our results, I've just taken some text from the Bayes theorem like Wikipedia page and just pasted it in here. Our training set is 5 documents for each language. Each of those documents is about 80 words. If you are familiar with machine learning, that's the worst training set in the history of machine learning. 5 documents can't tell us very much about anything, but this is text that is completely different from anything in our training set. This is just from Wikipedia, and you can see that it is insanely confident that it is English, which it is, which is great. And that happens, this is really accurate. 5 documents in each language, you're going to get this kind of result if you just go through and paste random news articles. Because naive Bayes is good at this. This is what it does. And again, language detection is the perfect problem because there is so much difference in the words in different languages. Makes naive Bayes' job really easy to just sort of say, like, okay, like, these are all English words, I know that, so like, you know, very, very probable versus these other languages. So that's the kind of result that we get. Here's a link. Again, you can find that in the slides. This is to a JS fiddle that has all of this code together, and you basically just paste in a little text box of any language from anywhere, and it'll guess it. Not any language, just the 3 languages. Again, we only care about those 3 languages. So you could, you know, do some tests and see how it actually does. That's me running that test on the Bayes theorem text. So that would be, if you are like me and you learn from actual like code and like making things, I would definitely recommend like having a look at that because it's very useful. Also, I've taken that for those of us that are JavaScript engineers and put it into like an NPM package for something else that I was doing, but now that exists in NPM. So we have this package here, and basically you can find it there, and that's what it does. So you just import, just like normal, this like Bayes class that we just sort of walked through here in JavaScript. Super simple. You can look through the source code. You have your classifier. You train it by just telling it, look at these words. This is all you do for training. There's 2 lines right here. So you would just loop through and just feed in each document that you have. And you tell it the label on the other end of that function. So we train it for French, train it for English, and then you have classifier guess, and it will again produce that object with probabilities along with it. So if you find that useful for anything or just want to learn from it, that link is where you can find that. Okay. Now we're going to go a little bit further. We're almost done here. I know I've been talking for a while. And say, what if we want to do this on a non-linguistic problem? Because I think that we just outlined pretty well how you would do this for that specific problem, which you could imagine how you do that now for spam detection, how you do that for, you know, it's also really good for sentiment analysis. Naive Bayes, really good for that. So you have some unknown text, you need to determine if the author of the text was saying something positive or negative. That, as you can imagine, is a really hard problem to solve because what's the difference between, you know, the word great in that context and the words not great? Again, this is naive Bayes, not genius Bayes. We're only looking at one word at a time. It's stupid, so it doesn't know that the word not is next to the word great, right? And so there's all kinds of like other stuff that you can do and get deeper into that. There's like tricks that people do for tokenization. One that I've read about is if you take any negative word, so you have the word not or no, and you take the word on either side of it and prepend an exclamation point to the beginning of that word. Now it becomes a different token. The algorithm understands it as a completely different word, and presumably, more often than not, that will have, you know, negative connotation along with it. So there's different things. You can imagine that one, sentiment analysis, is a very valuable problem in the world, and it's also a very difficult one. And so there's actually a lot of good written stuff about like using naive Bayes to solve that problem because, again, classification and language and that sort of stuff, that's what naive Bayes is really good at. So what if you want to do it on non-linguistic data, right? Well, as we saw, we have our algorithm is basically just a set of probabilities, right? So all you need is features. In this case, the features were just single words tokenized. So you need a set of features and then labels to go along with it. And then you also need the ability to know the probability of a given feature, which for us, remember in the example, was just knowing how often the word do showed up in a French document. So in this case, even if it's non-linguistic data like that, if you just have a way to know the probability that the thing that you have will occur in your data set based on your training data, then you can run naive Bayes on it. It gets a little more complicated, and truthfully, I'm not going to be great at being able to explain this because of the math side of it. But let's say that we have this problem, right? We have a table here of just like, you know, we're trying to classify, these are our classes here, male and female, and these are our features. We just have, you know, measurements here. We have height, weight, and foot size, right? Let's say that we ignore the fact that these two sets of data have nothing to do with each other. But maybe if you just took two, you know, let's say X and Y here are height and weight, and you just plot them over there, it would sort of look like that, I guess. So red being female and green being male. And so basically you know, the problem that you want here is you take a new set of data is incoming. We have height, weight, and foot size, but we don't know if it's a male or a female. So we want to take a guess if it's a male or a female. How do we do that? Well, if we go through the process that we just went through, the problem that you're going to run into is that what if we have, you know, something comes in and we see the weight of 175, right? That's not in our data set anywhere, so the algorithm has no awareness of it. Basically, what I'm trying to say is that the word example that we went through, every feature is discrete, right? Every feature is very specific. So the number 170 and the number 171, according to the algorithm, have nothing to do with each other the way that we just did it. So how do you actually do this? Well, you basically would look at, well, okay, so say that we have this blank dot here that is incoming data, and now we need to like classify it. Obviously, that's not in a good spot for us to easily classify it, but if that's the problem, that's what we need to do, right? So step one is that we would say, okay, we have a weight coming in, it's you know, 175 or whatever. We basically look at all of our, we're going to go one label at a time, just like we did with the French, English stuff. We're going to look at all of the male data that we have, all of the weight to go along with that, and basically have a way of sort of interpolating what the probability is that this weight right here would land in this set. So this is kind of on the edge, but you basically would want to come up with a probability 0 to 1 generally of what are the odds that this weight, you know, is going to be seen given this set of data. And again, you now look at the female side and say that actually looks more probable there because it's kind of inside that data there, but either way. So that's what you need to do. So how do you actually do that? That's the hard part that I can't even explain to you, but basically, as I understand it, you would draw these constants that are in here would come from your data set, and basically you would sort of model the distribution of your data. You would sort of look at, again, these circles that you're drawing here are sort of being like, what is the distribution, could we guess, of weight among female category and among the male category? And then based on that, we could plot our incoming weight right next to that and say, well, it's kind of on the edge, it's very low probability we'll see that in this distribution, or maybe it's right in the middle, very high probability that we'll see that in this distribution. Again, my point here, because I don't have code for this or anything, but my point is just that like that part is figure outable as long as you understand what you need to do. All you need to do is find the probability of a certain feature given your data set. So again, that's how you would use naive Bayes to do something that's non-linguistic. That is one of the classes that I mentioned in the beginning, Gaussian, naive Bayes, lots of different classes. That's basically assuming that, you know, we have a Gaussian distribution of data, and then we're going to like sample from that and draw our probability from there. So that's how you would do it, but but it's not necessarily something that naive Bayes is particularly good at, but I just wanted to cover that that is something that's possible to do, numbers and not discrete labels. But it's not like it's known for being the best algorithm for doing that. Another thing, semi-supervised estimation. This is another like sort of goes in the pros category of naive Bayes. This just as a real simple example. Imagine you have a set of documents that's labeled English and a set of documents that you have no idea what is labeled. And you want to make your model better. You don't have enough labeled documents. You want to label more of them. This is something that you could do with naive Bayes because, again, as we saw, the algorithm does not need very much data to actually be really accurate. So you can imagine you could set up something like this, right? You have your labeled documents. You use it to train your model. You then take the unknown documents. You bring them into your model there. And if they are classified with very, very high confidence, you could reasonably bring them back around and feed them into your labeled set, which seems kind of silly and like it wouldn't work because how do you not trust the, how do you like trust the model that much? But again, you could do it. You could set it so that like let's only classify 99% if we're like really, really sure. And then the benefit of that is that it could be, your model could be really, really sure off of only just like a couple words. And then if it's right, you get all the other words in the document now as part of your labeled data to go into your model, which now makes your model better, which means that you can train more unknown data, and you can imagine that becomes like a really powerful thing to sort of build a small amount of training data into a lot of it. Cool. Last thing, just talk about just breakdown. So what are the pros and cons of naive Bayes? Again, we know we use it for classification. It's really great for text classification. It's simple and fast. It's easy to understand. It can all be put in a JS fiddle. And training is really fast. It performs well on multi-class prediction. We didn't cover that at all, but if you wanted to label, put something in multiple labels at the same time, there's ways to do that. It does not need very much training data to work very well. We saw that. It performs really well with categorical data, so if that's what you're trying to do, use it. And it does that semi-supervised estimation that we just saw before. It's also great at active learning, meaning that when you have new unknown data sort of coming in, if you can get continuous feedback, so an example would be like, say you're using naive Bayes to do some kind of recommendation engine to take things like media that's tagged and like give it to your user, right? You're trying to recommend things for your user and you're using the tags off of it. If you can get feedback, you recommend them something and they will tell you if after you predicted it, if they actually do like it or not, then that's active learning. You can use that data now to go back into your model and make your model even better. So it's really great for that because of the way that the whole thing is structured. Cons, what are the bad things? It's a bad estimator. It's known for being a bad estimator. So that 99% probability of English should not be taken too seriously because it's just known for being sort of overconfident, I guess. For numerical data, as we saw, the probability has to be assumed in some way, so we interpolate the distribution off of the set, and that is not ideal because that's completely inaccurate, or probably is. The features that you have in the real world are often not completely independent from each other. It happens to work well for words, but often that might not be the case. And then as we covered before, the zero frequency problem is where you encounter a new word that you've never seen before. It's not in your training data. That can mess all kinds of things up. Ideally, you may want to estimate, or you have to really estimate the probability of seeing that new word that you haven't seen before. So that's a difficult thing to deal with when you're actually, that's something you'll probably come across if you're actually using this. That's it. And now, okay, I have an animation on this, I guess. Cool, here's just like a bunch of links that I would recommend. That book, these articles, there's the JS fiddle, there's the NPM package, and that's it. The end.